Okay, so yeah, I want to talk about reinforcement learning and routing and scheduling, particularly for the trucking industry. This is a little project we worked on over the summer with some of our interns from Rice, and I think is a neat application of reinforcement learning in industry on a problem. So I think everyone is aware how everything you get from the store came on a truck. It's a big deal. Truckers are one of the major employers of the United States and accounts for a large part of our gross domestic product with almost 3 million heavy truck drivers out there on the road. 3 million truck drivers, a large portion of those are heavy trucks. So it's a big deal to our economy and how everything works. It's also a very difficult problem. You can kind of imagining trying to solve the traveling salesman problem for many trucks and many orders at the same time. And if you're familiar with the traveling salesman, you might also notice that oftentimes there's no central depot involved when solving the trucking problem. A lot of these drivers out there just take as many orders as they possibly can and go all across the country and wherever the road takes them. So it's a problem in which perfectly solving it for more than a few days out or even a day out is oftentimes impossible. And I would say that this is the reason why there's more than 1 million shipping companies in the United States, many of them with 6 trucks or fewer. In fact, the vast majority are single owner-operator companies. What makes the problem so difficult is not just the permutations of orders and drivers, but you also have many, many restrictions you have to satisfy, whether you're trained or whether you have the equipment that's strong enough to haul the material, or even hours of service limitations, and getting home on time to visit your dentist. So, it would be lovely to tell you that this problem has been around for a long time and it's already been solved by computers, but it's just not the case. In reality, they haven't fully solved this problem with linear programming, and it's mostly done by dividing and conquering. You have a big room with people who specialize in certain areas, and they divide up the country and they divide up the orders, and they make a lot of phone calls and they write it down in notebooks, and then they make another phone call because they got it wrong. So it's a difficult problem even today. So reinforcement learning, I'll just talk about that for a little bit. I think this is a pretty advanced crowd, but for those who don't know, it made a big name a few years back now with AlphaGo, which was a great example of reinforcement learning to solve a problem that not that long ago nobody thought that computers could ever win and go. And yet here's this thing that learned by playing against itself, and now is virtually undefeatable. So it works by taking something like a game or an environment and interacting with it. Given a state, take an action, and then observe what's the reward, what happened when I jumped or moved right or moved left. At the bottom, this is the PDF version, there's a little example of cart pole where the video game, you have to balance the pole on top of a little hand that moves left and right and the pole falls over. And reinforcement learning does a great job of learning how to play these games. So we could do the same thing. We can make a game out of trucks driving around the country, delivering packages, and attempt to get the greatest high score of all time. The network is perhaps not too complicated, but you have a lot of things to keep track of, like how far you can actually drive legally, what orders you can take. Maybe you have competitors out there in your company. All these different considerations of what orders are out there, how to handle a large number of potential orders. And what we're hoping to learn with this network is that we're hoping to get a better knowledge of perhaps pricing, of what order destination pairs should be priced at, something about the geography of where orders go. We're hoping that we get an edge on the restriction handling. Maybe it's okay to put this load on a refrigerated truck because there's no one else available to do it, and and there's no loads for our refrigerated truck to take right now. So to do this, our interns and myself, we built this lovely tech stack with a web UI for the game and for exploring the orders and equipment available. We built a solver stack based on TensorFlow and NumPy, and we had essentially we had a couple of databases going, one which kept track of all the routes that were simulated throughout time and the assignments that were made. And then our feedback loop was that we would have a simulator which would run a simulation, assigning orders to trucks and running that out and storing the results in the database. And we'd also had a trainer which would pull results out of the database and try to learn from it, try to see what the value or estimate the value of a pairing of order and tractor, and spit out models which would go back to the simulator, which would get new results. And as you develop your model, you're actually changing your results. So you have to train again because new policies will get new results. And some of the results I can share with you is this is sort of a simple scenario we started with first, where we have a big box that is our region of the United States, where an order could just appear anywhere, right? It could appear in Nevada and deliver to Tennessee, or likewise, just randomly unbiased. And after running the simulator and training on it for a long time, we still found that the classic assignment, just look at how many miles you drove, how much money you make, still beats the reinforcement learning assignment. Again, this is actually just using the first heuristic, just kind of taking the greedy choice and not doing any kind of tree search to optimize. This is just take the first available. And I'm actually quite happy that we performed this well, that we're almost as good as a classic assignment, but we're not quite there yet. And I would like to say that the reason is because there's not a lot to take advantage of in this scenario. How can an estimator beat perfect knowledge of the system? So the next we did something a little bit more realistic. A lot of orders generate in Ohio and deliver to New York. You don't get a lot of traffic going back the other direction. So if we impose this on our simulator, and instead of randomly generating orders anywhere, we start generating orders more specifically pertaining to the real world, we start to see a different result. Now, actually, our heuristic with machine learning is beating the classic assignment. It's kind of figured out that maybe going to Miami is not that good an idea because you might not be able to get back very easily. And not only is it beating it in like just the raw revenue percentage, like the ratio of revenue to cost, it's actually producing significantly more completions. It's delivering about 11% more orders than the classic assignment. So it's showing a lot of promise in its development. So again, when we introduced the bias, when we started to be more realistic to the world and there was something to learn and something to take advantage of, we started to see better results. Maybe some of these things could have been implicitly learned. For example, if it costs more money, if they pay you more money to take an order to Florida, then it's probably a reason for that. But this was able to learn it sort of agnostically, and I think that's quite a nice finding. And again, I would like to say that that's largely because the classic way to solve this by simulating it is a perfect solution, at least in the simulation terms. It knows exactly how many miles you drove and exactly how much you'll get paid for it. It's hard to beat that when there's not any biases to take advantage of to learn from. A few things we could go further is testing with more and more of the restrictions that we could add in. We need to still hypertune our model so that we could outperform in more scenarios. We could even hypertune the kernel that looks at the historical orders to build a reward estimate. And another thing is working on interpretability so that the users get a better understanding of why they're sending their trucks to particular destinations when they would have chosen a different way. Of course, just a few little fun things to add is that we generated quite a bit of data, overflowed a few hard drives, and off by one errors in data science are even more fun than standard development. I don't know if any of you have run into that problem, but it's a good one. Otherwise, I'd like to thank my fellow co-authors, Graham Gansel, Daniel Fay, Brian Thompson, and Emmett Bertram, who also helped on this project. And if you have any questions, you can reach out to me this way. Thank you.
Questions?
Hi, you mentioned that this particular type of routing problem it's been unsuccessful to solve it with like a linear programming. What about a mixed integer linear programming? Has there been any success there?
It definitely happens, and it's definitely in use out there. But so many times I've interviewed a few companies that they'll use that and they'll look at the results, and half the time they'll kind of discard it. They'll take it away. So it is out there and it is effective, but it still hasn't quite overcome some of the situations they've found that have been so difficult to encode.
Okay. Well, I mean, it's a lot of constraints that makes the
Right.
model quite large. So I didn't know if it was a time, if the issue was the time to solve, or if it was just the results weren't quite, didn't quite work or not.
Yeah, it's definitely both. That it does. I think there was one user out there that had something that took like 30 minutes to solve, and that was actually too long for them. And also, sometimes they just didn't agree with the results. They said, I would have sent this to here, and you should have done it like that. And it doesn't have good enough feedback for why.
Yeah, well, it's a rather hard model to put together, even for a really good solver.
Yes. Yes. Thank you.